think we're going to continue with Chapter 5. This is where we left off, doing calculations. So this is their version of our stoichiometry roadmap. You can see it's pretty similar. To go from grams to moles. You go from grams to moles, you divide by the molar mass. Going the other way, moles to grams, you multiply by the molar mass. And then going from moles to moles, you're going to use what they call the mole-to-mole conversion factor, and we call the coefficients from the equation. And this is from the previous problem. Well, let's go down here. Now we're going to start a completely different topic. Oxidation and reduction. Oxidation normally is the loss of electrons from an atom. Reduction is gain of electrons by an atom. You have to have both of these together. You can't have one without the other. So you already have oxidation, you have reduction. If something's losing electrons, something has to gain the electrons. Short version of them are called redox equations. An easy way to remember it is using this mnemonic. Leo the lion says grr. So Leo, loss of electrons is oxidation, and grr, gain of electrons is reduction. So if you go on, or later on when we get to chapter 15, we talk about organic chemistry, it's not quite as obvious. There's other ways you could talk about oxidation and reduction. But for now, this is the definition we're going to use. So here, if we put a zinc strip into a copper 2+ solution, you went to Home Depot and bought copper sulfate, which is root killer, if you have roots in your sewer lines and you want to get rid of them. You make a solution out of it. It's a bright blue solution. If you stick a zinc strip in there, the zinc is going to lose 2 electrons, become Zn2+. The copper 2+ will gain 2 electrons to become copper solid. You will actually see solid copper plating out on the zinc strip. So if we look at the equation, we have zinc solid plus Cu2+ goes to the Zn2+ plus Cu. So you can see the zinc loses 2 electrons. It's oxidized. Because the loss of electrons is oxidation. The Cu2+ gains 2 electrons, so it is reduced. So we can break up this reaction, what are called half reactions. So if you just look at the zinc half, you can see the zinc goes to Zn2+ plus 2 electrons. So it's lost 2 electrons. Cu2+ gained 2 electrons, it goes to Cu solid. The thing that confuses a lot of people, the thing that is oxidized, in this case the zinc is oxidized, is called the reducing agent. And the thing that is reduced is the oxidizing agent. So zinc is being oxidized. It's causing the Cu2+ to be reduced. So it's the agent of reduction of the Cu2+. So all you have to remember is whatever is being done to it, if it's being oxidized, it's the opposite. It's the reducing agent. If it's being reduced, it's the oxidizing agent. That's all you really need to know. So a compound is oxidized by causing another compound to be reduced. It's called the reducing agent. So zinc was oxidized, so it's the reducing agent. Compound that's reduced by causing another compound to be oxidized is called an oxidizing agent. So here, Cu2 plus is the oxidizing agent because it makes the Zn, causes the Zn to be oxidized. Perfectly clear? So here we see some examples of oxidation reactions. You notice they're all losing electrons. Here are reduction reactions. All gaining electrons. Notice that chlorine and oxygen gain electrons. So they're reduced, so they're oxidizing agents. Where do we find chlorine and oxygen as an oxidizing agent? Sometimes. I'm thinking of something. Chlorine. People wash clothes? Chlorine. Clorox, which is a...
No swipe. It takes out, removes stains.
Clorox, you don't want to spill it on your clothes. It's a bleach. Oxygen, OxyClean. So they're oxidizing agents. They're being reduced. So what happens when you have stains on your clothes, the color from the stains is due to the organic compounds in there, a certain structure. When you add the chlorine or the oxygen, it causes those stained colors to be oxidized. When they're oxidized, they lose their ability to show color. So you see right through them. So the stain is gone. Even though the material is still there, it's gone. Okay? Hydrogen peroxide is an oxidizing agent. Where do we find hydrogen peroxide? I mean, obviously for cuts. Where else do you use hydrogen peroxide? Ladies? When I say ladies, and you answer. Okay. Bleaching your hair, yes. Iron rusting is an oxidation process. Iron loses electrons. If we look at the compound here, iron, any element by itself has an oxidation number of 0. So if I look here, iron has an oxidation number of 0. Oxygen by itself, it has an oxidation number of 0. Now we go and look at the compound Fe2O3. Oxygen always has what charge? Oxygen in a compound. Look at your periodic table. It's in column 6. So it has a charge of -2. So oxygen over here will become -2. Iron in this case is going to be what? Remember, the whole thing's got to balance out. So if I got -2 for oxygen and I got 3 oxygens, that's a total of -6. So I got to have +6 on this side. If I only have 2 irons, each one's got to be?
I don't even know.
No. What's 6 divided by 2? 3. Iron is 3 plus. See here we see iron goes from 0 to 3 plus. So it's losing electrons. Oxygen's going from 0 to -2. It is gaining electrons. So oxygen's being reduced. Iron is being oxidized. Oxygen is being reduced, so it's the oxidizing agent. Iron is being oxidized, so it's the reducing agent. Okay? Okay. People who have a pacemaker have a lithium iodine battery in it. So here we have lithium and iodine. So lithium's by itself, so it has 0. Iodine's by itself, it has 0. Here in the compound, lithium iodide, lithium is a charge, +1. Iodine is, no, it's got to add up to 0.
-1.
-1. So lithium is going from 0 to +1, so lithium is losing electrons. It's losing negatives. Iodine is going from 0 to -1, so iodine is gaining electrons. Iodine is being reduced. Lithium is being oxidized. So iodine is the oxidizing agent. Lithium is the reducing agent. Where else do we use iodine in medicine? Yeah, well, betadine. All right. You guys are probably too young to remember, but when I was young, if you got a cut, your mother put tincture of iodine on there. And it would burn like crazy because A, the alcohol makes it burn, and the iodine is an oxidizing agent. What else do you put on cuts? Hydrogen peroxide. So I already told you hydrogen peroxide is an oxidizing agent. So that's how it helps disinfect wounds, and that it oxidizes all those little bacteria, chews them up. Although now they're saying hydrogen peroxide doesn't do that as well, just the foaming action kind of lifts the dirt out of the wound. So. People who go camping and you want to drink the water out of the stream, you know, you can buy these little pills, iodine tablets, because iodine, why does it clean it? It oxidizes. It's an oxidizing agent. So there's your little pacemaker sitting in there. And if you ever know somebody who dies and you want to cremate them, they'll ask you if they have a pacemaker because it has to be removed before you cremate somebody. They tend to explode when they get hot. They frown on that. So that's what we're going to talk about, oxidation reduction. If you go on to take 131 or 151, we'll go into it in more detail. So energy. When molecules come together and react, bonds are broken in reactants, and new bonds are formed in the products. So break a bond, if you hadn't realized it, always requires an input of energy. To break anything, you got to supply energy. Bond formation releases energy. So if I'm going to break this chlorine-chlorine bond, I have to add 58 kilocalories per mole of energy. That's how much energy I have to put in. If I form a chlorine-chlorine bond, I'm going to release 58 kilocalories per mole. The actual number is not really important. Just the breaking bond requires energy, forming a bond releases energy. There's a term called delta H, which is enthalpy. H is enthalpy. So delta H is the energy absorbed or released in a reaction. It's called the heat of reaction or the enthalpy change. So anytime you do a reaction, you can either give off heat or absorb heat. Okay? When energy is absorbed, the reaction is said to be endothermic. Delta H is positive. So, a reaction that absorbs energy, you can think of those chemical ice packs where you got the little bag inside the big bag and you pop the little bag and you shake it and it gets cold. Well, feels cold to you, because that reaction absorbs energy. And if you're holding it, where does it absorb energy from? Your skin. So as you remove energy from your skin in the form of heat, it feels cold. Energy is released, the reaction is said to be exothermic, and delta H is negative. So you can think of an exothermic reaction, a firecracker. As soon as that ignites and it reacts, it goes boom, releases a lot of energy. So if we're going to break this chlorine-chlorine bond, the delta H would be plus, endothermic. If we form a chlorine-chlorine bond, the delta H is negative, exothermic. So if you look at the total delta H of a reaction, depending on if it comes out negative or positive, delta H indicates the relative strengths of the bond. When delta H is negative, more energy is released in forming the bonds than needed to break the bonds. Remember I said chemistry, or chemical reactions, you're breaking bonds in the reactants, and you're forming bonds in the product. So if the energy released in forming the bonds is greater than the energy needed to break the bonds, you have energy left over, and that's released, so that's exothermic. So here we're taking methane and oxygen going to CO2 and water. Okay, this is natural gas being burned. The delta H is negative 213 kilocalories per mole. Heat is released. Okay, you probably could have figured that out because if you have a natural gas furnace, the furnace does what? Supplies heat. Where does the heat come from? It comes from this reaction. If delta H is positive, you need more energy is needed to break the bonds than is released in the formation of new bonds. So here we have carbon dioxide and water giving us glucose and oxygen. It requires 678 kilocalories per mole to do that reaction. Does anybody know what that reaction is? Taking carbon dioxide and water and making glucose and oxygen. If I said you needed light to do this reaction. Photosynthesis. So that's what the trees do. Anything else needed for photosynthesis? A little pigment. Begins with a C. Chlorophyll. So now this time of year, the trees are ready to go dormant, so they're stopping their photosynthesis. So the chlorophyll is going away. The color of chlorophyll is green. So when the green goes away, you see the other compounds that have always been there, the carotenoids. Guess what color carotenoids are? Orange. And some of the other ones that supply the reds and the yellows, so that's why the leaves turn color in the fall. Disappearance of the chlorophyll. So, in an endothermic reaction, heat is absorbed. Delta H is positive. The products are higher in energy than the reactants. Exothermic, heat is released, delta H is negative. The products are lower in energy than the reactants. So going back to my favorite thing, which is chocolate chip cookies. All right, I put all the ingredients together. Now I'm going to bake it. So there's chemical reactions going on. Is that an exothermic or endothermic process?
Endothermic.
Endothermic. I got to supply heat. I'm not sure I'd want chocolate chip cookies that give off heat after they're done, but. So, energy diagrams. We can diagram what this looks like. Here we have a molecule AB reacting with an atom C to go to an atom A plus a molecule BC. So we're breaking an AB bond and forming a BC bond. So we can do what's called an energy diagram. Plots energy on the vertical axis and the progress of the reaction on the horizontal axis. So here, we have the reactants on the left, the products on the right. Here the products are lower in energy than the reactants. So this is an exothermic reaction. Well, here we have something called energy of activation, E sub A. What does that mean? Well, when you're going to make a fire in a fireplace, now fall's coming, and you put logs in the fireplace. Okay, fire in a fireplace gives off heat, so it's exothermic. But do the logs spontaneously burst into flame when you put them in the fireplace? No, you have to do what? You got to heat them up. You got to use match and kindling and all that. You got to provide a certain amount of heat until they light. Once the logs are on fire, you don't have to do anything. You just sit there. So that heat you provide is this energy of activation. And right at the top is the transition state where it goes over from being endothermic to exothermic. So if you look at this, you kind of think of this, what does it look like? A what? A roller coaster. So if you go on the old-fashioned roller coasters, you know, and you get in those cars, they have a little motor that chugs you up to the top. So you're putting in energy. Click, 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 till you get to the top. Then you get to the top, it releases you. It's not putting in any more energy. Now you're giving off energy all the way down due to gravity.
So that's kind of like essentially like potential kinetic type of thing, or is that just a different analogy?
It has a role in kinetics. This is more thermodynamics, and they're all related. So this is an exothermic reaction. Right here, the difference between the reactants and the products, this is your delta H. And you see if I subtract the products minus the reactants, and this is a smaller number, I'm going to get a negative. So delta H is negative. So the energy of activation is the minimum amount of energy that the reactants must possess for the reaction to occur. It's called the energy barrier. And the height of the barrier determines the reaction rate. So there's where your kinetics come in. So you can imagine the higher the barrier, the slower the rate. Yeah, if we were to run, the class were to run a race, 100-yard race, and in the middle I put a hurdle that was 1 foot high, it would take you a certain period for everybody to go across. If I raised that barrier to 3 feet, it would take you longer. And if I raised it to 6 feet, we probably would never make it, but it would take us a longer time.
What page is that on?
I don't know. Anybody know what page that's on?
Starts at 171 and goes to 172.
Okay. 171 to 172. Yeah, 171. Okay. So when the energy of activation is high, few molecules have enough energy to cross the energy barrier, and the reaction is slow. Again, if we're running a race and I have that 6-foot hurdle, there's going to be fewer of us that can make it over that 6-foot hurdle or 6-foot wall than if it was a 1-foot wall. When the energy of activation is low, a lot of us can get across, so the reaction is fast. The difference between the reactants and the products energy is called the delta H. If it's negative, the reaction is exothermic. And here you can see we have a lower energy barrier, lower of energy activation. But that varies from reaction to reaction. Obviously, lighting a log in a fireplace has a higher energy of activation than, let's say, lighting a firecracker. Once that stuff inside the firecracker, the gunpowder mixture ignites, it's a relatively fast reaction. If the products are higher in energy than the reactants, delta H is positive, and that's endothermic. That means you have to keep supplying heat to get the reaction to go. You kind of think of like frying an egg. You start to heat it, it just starts to turn a little bit white, and you take it off the heat right away. What's going to stop cooking? You have to keep heating it to cook it all the way. You know, Thanksgiving's coming out, you wouldn't want to stick your turkey in the oven at whatever it is, 350 degrees, and after 15 minutes pull it out and eat it. Reaction rates. Okay. How can concentration and temperature affect reactive rates? Remember, to react, the molecules have to collide. So, if I increase the concentration, if I have more molecules present, what do you think is going to happen to the rate? It's going to increase. There's more chance of the molecules hitting each other. Now, if I had this room and I put like 3 people in this room and you blindfolded you and you'd have to run around and bump into each other, it's going to take a while. But if I blindfolded everybody in here, we got like 25 of you, actually more than that, and you ran around, you're going to hit somebody a lot sooner. Increasing the temperature is not only good enough to hit each other, you have to hit each other with enough force. You know, if we walk down the hall, I come around the corner, you come around the corner, we're just kind of moseying along, we bump into each other, it's, oh, excuse me, and we go on our way, nothing happens. If we both are running as fast as we can and we hit at that blind corner, something's going to happen. So you increase the kinetic energy when you increase the temperature, you increase the speed of the molecules. So you're also going to increase the reaction rate. More molecules are moving fast enough to get an effective collision. What about catalysts? Catalysts speed up reaction rates. How do they do that? And they don't take part in reaction. They're recovered unchanged. What do? They lower the energy of activation. They don't affect the delta H. They just lower that energy barrier. So, here's our reaction. I blindfold everybody. The goal for the reaction is everybody to get out the door. You guys are going to stumble around. Eventually, everybody's going to get out the door. Now, I blindfold everybody except one person. That person's not a catalyst. What is that person going to do? That person's going to grab everybody and take them to the door or throw them out. Okay? That's going to go a lot faster. Start and the end of the reaction are the same. You all started blindfolded, and in the end, you're all out the door. The catalyst all does lower the energy of activation. Give me an example of a catalyst.
Baking soda and cookies.
Yeah.
You make the cookies.
Catalytic converter.
Catalytic converter in a car. How about a biological example? Enzymes are catalysts. So here we're looking at a catalyzed versus uncatalyzed reaction. all we did, we end up at the same place, we start at the same place, but we lower the energy of activation. Okay? So it's faster. So, catalytic converter in your car uses a metal catalyst, rhodium, platinum, or palladium, which are very expensive metals, which is why people steal catalytic converters. And what they take is the unburned parts of gasoline and react them inside the catalytic converter, so it comes out as nitrogen, water, carbon dioxide, and oxygen. And a catalytic converter, since it's burning, gets very hot.
Like a reburner, right?
Like a what?
Like it reburns it.
Yeah, it takes the unburned part of the gasoline and burns it. It lowers that activation energy of burning, so it burns all the byproducts. So if you've ever driven your car anywhere and gone underneath and accidentally touched a catalytic converter, you'll find out it's very hot. They put shields underneath because in the past people have ridden around and parked over a pile of leaves, and they set their car on fire. Equilibrium. Right now, up to this point, we've been talking about reactions that go from left to right. Well, a lot of reactions go from left to right and right to left. They go in both directions. It's a reversible reaction. Forward reaction goes left to right. The reverse reaction goes right to left. The system is at equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. The net concentration of reactants and products do not change at equilibrium. What does that mean? Okay. This drawing should be obvious to everybody. What do we see here? These are goldfish in a tank. All right, now you can see why I'm not in the art program. Okay. So we start off with 5 goldfish on the left side of the tank. And we go away and we come back. After an hour, we see 4 goldfish on the left, 1 on the right. We go away again, come back, we see 3 on the left, 2 on the right. And every time after that we come back, we always say 3 on the left, 2 on the right. We've reached a state of equilibrium. So whenever we come back, we see 3 on the left, 2 on the right. Now, are they the same goldfish each time? Not necessarily. When one goes to the left, right, one comes back to the left. So they keep swimming back and forth, but they prefer to be 3 on the left, 2 on the right. So the process hasn't stopped. Goldfish haven't stopped swimming. It's just that they prefer to be in a certain orientation. That's equilibrium. The key is equilibrium. The reactions don't stop. The forward equals the reverse. So another example. She has $10, $1 bills, and I have none. She gives me one, now she has, I have one. She gives me another one, I have, she has. She gives me another one, I have, she has 7. She gives me one, I give her one back. Now she has 7, and I still have 3. She gives me one, I give her one back, she has, and I have 3. We do that for the next 24 years. At the end of that 24 years, she has, and I have 3. We've reached equilibrium. Doesn't mean 50-50. It doesn't mean 5 and 5. That it could be 7 and 3. It could be 6 and 4. It could be 9 and 1. But we've reached that steady state where the forward equals the reverse. So we're going to talk about Le Chatelier's principle. Basically, he said if a chemical system in equilibrium is disturbed or stressed, the system will react in a direction that counteracts the disturbance or relieves the stress. Simple. It's the old teeter-totter at the playground. So here we have carbon monoxide and water going to carbon dioxide. So here's our teeter-totter. Right now I'm going to put CO O2 on this side, CO2, I'll put 2 there, and 2 there. So we're at equilibrium. If I add carbon monoxide, what's going to happen to the teeter-totter? It's going to tilt. So here I have my CO2, CO02. Now to bring it back to equilibrium, what do I have to do? I'm going to have to shift some of this to the other side. Right? So I'm going to shift this in this direction. So I ended up with CO2. So by adding more carbon monoxide, I'm going to increase the amount of, ultimately, carbon dioxide. I'm going to shift everything to the right. So if I add more reactant, I'm going to end up with more product. Kind of makes sense, right? I got more stuff to react, I'm going to end up with more product. Okay. What happens if we add CO2? If we add CO2, it tilts the other way. To bring it back to equilibrium, which way do I have to transfer the weight? I have to transfer it back this way. So if I add CO2, what I end up is getting more reactant. It goes back the other direction. Yes, no, maybe, oranges. If you add a reactant, everything shifts to the right. You gain more product. If you add a product, everything shifts to the opposite side. You gain reactant. If you remove a reactant, everything shifts towards the reactant. If you remove a product, everything shifts towards the product. So if you add something, it moves, the equilibrium moves to the opposite side. If you remove something, the equilibrium moves back to the same side. So in this one, what happens, we're taking ethanol and making ethylene in water. If I remove water, what am I going to do?
But you gotta remove something on
No, you can't. You can only shift stuff. No. If I start, here's my ethanol. If I remove some of this, it's going to tilt which way? It's going to tilt this way. So to bring it back to equilibrium, which way do I have to shift? To the right. So I end up making more product. I shift the reactants towards the product side if I remove something. So remember what I said, if you remove something, the equilibrium shifts towards the same side. If I add something, it goes to the opposite side. Here I'm removing. So I'm making more product. So adding reactant favors the products. Removing reactant favors the reactants. Adding product favors the reactants. Removing product favors the product.
I understand, it seems like it's almost reversed. What if I could dumb it down even more for me, I'm not sure. It's this weekend, the wife made some cleaner, bathroom cleaner, baking soda and vinegar.
Okay.
And she put some soap